Now, how do we balance redox reactions? We use what we call the half reaction method. In the half reaction method, we write the oxidation half reaction and the reduction half reaction and individually balance them. It is also important to note the pH of the solution in which the redox reaction is taking place. Is it in an acidic solution or is it in a basic solution? For this example, the redox reaction took place in acid solution. Let's go through the steps one by one. So the first step is to write your oxidation half reaction, which we identified as iron 3 forming or iron 2 forming iron 3. The reduction half reaction involves dichromate ion forming chromium 3 ion. The next step is to balance the atoms in both half reactions. If we look at the oxidation half reaction, we see that the number of atoms are already balanced, so we don't need to introduce any coefficients. However, in the reduction half reaction, first we look at chromium. On the left side, we have 2 chromiums, but on the right side, we only have 1. So we write a coefficient of 2 for chromium 3. Furthermore, we notice that there is oxygen in the reactant side, but no oxygen in the product side. We balance this by adding water molecules. So we write 7 water to account for the 7 oxygens in the reactant side. By adding water, we now introduce another element in the half reaction, hydrogen. How do we balance the hydrogens? And this is where the information of the solution's pH comes in. We know that this redox reaction takes place in acid solution. So we use hydrogen ions or H+, which are abundant in acidic solutions. So we add 14 hydrogen ions in the reactant side to balance the hydrogens in the product side. This is step 2. So step 2 involves balancing of atoms. Now we go to step 3. In step 3, we balance the charges, and this is where we will see electrons. We will use electrons to balance the charges in both half reactions. Let's start again from the oxidation half reaction. The total charge on the reactant side is positive 2, while the total charge on the product side is positive 3. To make the charges equal on both sides, we need to add 1 electron on the product side. This makes the net charge of the product side equal to positive 2, hence the charges are balanced. Let's go to the reduction half reaction. If we look at the total charge on the reactant side, we have 14 times positive 1 plus 1 times negative 2. So the total charge is positive 12. On the product side, we have 2 times positive 3 plus 7 times 0. So the total charge is positive 6. This time, we will add electrons on the reactant side. 6 electrons to be specific. If we add 6 electrons, then the charge now will become positive 6 also on the reactant side. So the charges are now equal. That is the third step. The fourth step is important. In the fourth step, we maintain what we call the electrical neutrality of the solution. This simply means that the number of electrons provided by the oxidation half reaction must be equal to the number of electrons needed by the reduction half reaction. So if we look at the number of electrons, in the oxidation half reaction, we only have 1 electron, but in the reduction half reaction, we need 6 electrons. So this can be solved by multiplying the oxidation half reaction by 6. This gives us a new oxidation half reaction involving 6 iron 2 forming 6 iron 3 plus 6 electrons. Now that the number of electrons are balanced, we can now add the two half reactions, and this is step 5. Let's add the two half reactions. We have 6 iron 3 plus 14 hydrogen ions plus dichromate, forming 2 chromium ions or chromium 3 ions plus 6 iron 3 ions plus 7 water. Notice that we no longer see the electrons because they will cancel out. Anything that appears on both the reactant side and the product side of chemical reactions that are added cancel out. So in the final step, we just need to check if the atoms are also balanced. So we have 6 irons on both sides. We have 14 hydrogens on both sides, 2 chromiums, and 7 oxygens. And this is now our balanced redox reaction for the oxidation of iron 2 ion by dichromate.